you, Marcus. Good afternoon, everyone. I'm Anil, and this is work with my collaborators, Alessandro and Michael. They have done all of the hard work, and they've entrusted me to come and spread the word. So let's start with a little bit of a scenario to motivate this work. Let's assume you're a Go developer and you're writing an antivirus engine, and the AV really needs to decompress incoming files to be able to inspect them. And you have the choice. Given that you're writing in Go, you either pick the Go decompression library written in native Go, memory safe, or you pick the well-tested C library. So this choice, the conventional wisdom is that you would go with the C library because it's faster. You would go with the Go library because it's memory safe. So maybe you should use Go for more security. But we've asked ourselves, what about the non-memory corruption vulnerabilities, and what if this really holds that we should use the Go version for more security? So this is where parser tree differentials come in. We have essentially, because we have these two libraries that have been written by independent developers, they will have different parse trees, slightly different, and those little differences may result in security relevant consequences. So it may be that, for instance, one of the parsers may be overly strict for some of the inputs. It may also be that it might be overly strict, overly liberal. And also it might be that neither of them are really buggy. They're all conformant to the specification, but it's just that the specification is underspecified and leads to security issues, of course. So this is why we've used differential fuzzing. What is differential fuzzing? I don't really need to introduce it because we had a nice introduction in the keynote. However, for our case here, we have our inputs that are generated by the fuzzer, and they will be provided to the two different versions of a program. In this case, the same library, either written in the C language with C-Go bindings used through Go, or the one that's natively written in Go. And the important part is that the outputs of these, we have some oracle that will compare the results of the parsing, right? And the interesting cases are the cases where we see some difference, right, in the behavior between the two libraries. So we did our evaluation. We chose 4 libraries. The criteria for choosing them was that they would be parsing libraries, preferably with some sort of security sensitive application. So we've chosen ASN1, X509, the libz compression library, and the PNG image parsing library. We also needed for them to be widely used C libraries and easy to write harnesses for us to be able to test them for the differential fuzzer. What you can see the sort of quickly in the results. So here on the left-hand side, we have the unique differences over time and over multiple runs. So each color is a different run by resetting the fuzzer into a clean state. And you can see that's fairly effective, although we did not try to optimize this differential fuzzer in any way. So we were able to find interesting bugs, and I'll discuss one of them. Here's the libz use case. On the left-hand side, you have some compliant input with the 7-8 header. So the important is that we have this 7, which is smaller than 8. And in the mutated input, we have F, and this is actually non-compliant according to the specification. And so the right behavior is to fail the uncompression of this input, which the C library does properly. However, the Go library happily uncompresses the data that follows by treating it as properly formed input. So what's the security impact? We've given one scenario. Let's assume we have an attacker and they have their malware and they want to bypass an AV scanner. So they put it inside of an archive. And then the AV scanner here, let's assume it's written in C. We'll be decompressing that file. We'll try to check it. But if we pass it with our mutated input, the AV scanner will say, well, this is malformed when it tries to decompress and use the libc library. And it will say, okay, given that's malformed, that's not a compressed archive, so we can let this file go through, right? However, the victim will be using the Go library, and Go library will happily decompress the files, and we will be delivering our malware, right? So we asked ourselves, is this really true, or is this the case that the AVs would not decompress our files and mark our file as benign? So we've put some malware, we've compressed it, and then we did that mutation we found with our differential fuzzer. And 0 of the AVs on VirusTotal find the malware, whereas if we don't do the mutation, we have 22 AVs that accurately identify the file as malware. So we can bypass those 22 AVs. The same is also valid for Gmail. We quickly tested uploading this file before sending. Gmail will scan the inputs and check whether there's any virus in the emails that you will be sending. And of course, if it's corrupted, and that's the correct behavior, right? It will not identify the malware. Right. So in the paper, we have lots of additional results. We looked at other bug-inducing differences in the other cases. Specifically, we also have some security impact on the certificate transparency use case. We also discussed practical implementation challenges, namely to get our differential fuzzer to work with Go and C libraries. And we have a study of the prevalence of C and assembler code in Go programs, just to say that this is something that happens very often, that people use C in Go programs. So you can check out the paper, and I will conclude with the takeaways of our work. As a library user, I would say that we can give the following recommendation: to be careful, because the native libraries are not necessarily more secure. It entirely depends on which setting you will be using those libraries. And of course, there are settings where it can be very dangerous to have 2 distinct parsers that are used. And as a library writer, it's also always a good idea to use now differential fuzzing if you have a new version of a library to find bugs in your code. All right, so this concludes my talk, and I'll be happy to take your questions.
All right.
I have 2 questions, actually.
Yep.
The first question is, did you use in-process fuzzing for comparing Go and C libraries?
Yes.
Okay. Yeah. And you did this via...
So we based it on GoFuzz. GoFuzz is the native Go way of fuzzing Go programs.
Yeah.
Unfortunately, GoFuzz didn't have any support for fuzzing C code through C bindings at the time where we did this work. And actually, we had to do a lot of hacks to get that to work. But now, since Go 18, you can also do that. That's also a nice thing. Nowadays, you don't need to do that.
Okay.
Those hacky changes, yeah.
Great, thanks. And the other question I had, so one thing that came to my mind when you mentioned those parser differentials,
yes,
is URL parsers. I think there it's a big problem. Did you consider this use case?
We did not look at that, but yeah, I would expect also similarly that you may have parser differentials there. Yeah.
Right. Thanks.
Okay, I think we have time for one other question, if there's any. Yeah.
Thanks for the talk. I'm wondering, do you see some solution going forward? Like, should we get all the parsers, try to get the kind of a to be as broad as possible so they all parse the same thing, or to be on the other side, like needs to be as constraining as possible? Because this problem we have also with p-loaders and other file types. Do you see some direction forward?
Right. So I mean, a great question. I don't think it's necessarily the best of ideas to say we should be more tolerant of the inputs, because that tends to lead to also lead to issues, right? So I think it's a question of, it's the same with memory safety in general. There's not like one very easy solution, but there are techniques, namely fuzzing, but there are also static analysis techniques that will allow you to identify those differences in the parse tree. And this is what I would say make the most sense, because there will be a lot of settings where indeed the code will be slightly different. Can also be different versions of the same library and so on and so forth, right?